All right, hey everyone. We are back with another science lesson. Today we're going to do a couple notes here and a worksheet that goes with them. So today we're going to look at the atom. And atoms are the building blocks in which all matter on Earth is made. You may recall that at the side of the classroom we had a big periodic table, and I drew your attention to it a few times. And I mentioned how on that periodic table are all the elements known to man. And what they are is I kind of equate them to the Legos of the world. So all those elements are different Lego types, and we can put those together and build things. So in your house, you may put together a bunch of Legos and create a car, and then you may pull them all apart and create a house, and pull them all apart and create a spaceship. So the same Lego pieces, if put together with other different Lego pieces, can make different things. And that's kind of like the elements. The elements can be put together or taken apart to make things. We don't make new Legos, and we don't destroy Legos. And what I mean by that is all the elements that are on Earth, we have a certain number of them in the trillions and trillions and trillions and trillions, so many zeros you couldn't even understand. But we don't make new elements, and we don't destroy new elements. All we do is we put them together to make things, and sometimes take them apart. So we can take those elements and we can put them together and make salt, or we can make vinegar, or we can make plastic, or we can make whatever. So those are the elements. And we're going to look at what those elements look like. So one element is gold. If you look at gold, just one gold atom, what would it look like? If you looked at one sodium atom, what would it look like? So we're going to go over that today. And I didn't mean to do this, but suppose you have the element gold. So imagine taking that gold ring that you have and you cut it into half, cut it into half again, cut it into half again, cut it into half again. Eventually you're going to get down to, say, there's 4 atoms. Then you cut that in half and there's 2 atoms. And you cut that in half and there's 1 atom. Once you get down to 1 atom, the smallest piece of gold you can have, and this is so microscopic that you can't even see it, even quite often with a microscope, that you have a gold atom. And it's the smallest piece of anything that you can have. Now, if you recall last day too, we talked about how atoms make up everything. Now this here is what an atom looks like. So in the middle here, it has what's called a nucleus. And that nucleus is made up of protons and neutrons. Now, we talk about things having charges. Magnets have a charge. One end is positive, the other end is negative. And opposites attract when it comes to charges, and that's why magnets can stick together. Or if you've ever tried to put 2 positive ends of a magnet together, they will repel each other. They push apart. They don't stick to each other. But that's an example of a charge. And in an atom, atoms have charges, or parts of an atom has a charge. So in the nucleus here, we have protons. And you can see right here, number 1, protons. These are parts of the nucleus that have a positive charge. And we also, in that nucleus, have neutrons. And neutrons have a neutral charge. They don't have any charge. It means they're neutral. And around the outside here, going around and around and around the nucleus, just like a planet Earth going around the sun, these little yellow things, they're not yellow in real life, but these little things are called electrons, and they have a negative charge, and they just orbit around. Now, in an atom, the following is true. First of all, the number of protons is equal to the number of electrons. What that means is, in this case right here, we have 1, 2, 3 positives. So these little green things, 1, 2, 3. 3 positives. We also have 3 electrons. So the number of protons and electrons always equal to each other. And that's actually what makes the atom neutral overall. So the atom is neutral. It has positive pieces to it, it has negative pieces to it, but because the positives and the negatives always equal each other, it is neutral overall. Number 2, the number of protons is called the atomic number. So I'm going to flip over to another note here, the periodic table, and you can see right here the number 1, above lithium the number 3, above beryllium the number 4. That is the atomic number. And atomic is just a fancy word for the atom's number. So that is the atomic number, the atom's number. And what it's referring to is how many protons it has. So I'm looking here, and I can see 1, 2, 3 protons. That tells me that we are dealing with lithium. Right here, lithium has atomic number of 3. It has 3 protons and must be lithium. If we can see here, magnesium has an atomic number of 12. What that means is, if this picture here had 12 protons in the nucleus, that would tell me that it's magnesium. So that's how we tell one atom type from another, how many protons it has. Only lithium has 3 protons in its nucleus. Only gold has 79. Only magnesium has 12. Only hydrogen has 1. So that's the atomic number. Now, as I said, electrons are negative, and they orbit around the nucleus, which is in the center. So there's a bit of an insight, and just to go back and remind you, the number of protons, the pluses, and the electrons, the negatives, are always equal to each other. So if this was magnesium, and it had 12 protons in the nucleus, that would tell me that there would also be 12 electrons orbiting around the outside. All right, moving on to the periodic table. So the periodic table is this table which displays all the elements. And there is an order to this periodic table. And the order is by its atomic number. So you can see here, hydrogen is 1. Helium has 2 protons in its nucleus. Lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, sodium 11, magnesium 12, aluminum, silicon, phosphorus, sulfur, chlorine, argon, all in order by their number of protons. The periodic table, we might get into this a little bit more coming up, but the periodic table is this weird shape because not only that, but we have columns here, and all the elements in that column act the same. So everything in this first column here, we call these the alkali metals. They all act the same. And that's why we get this big gap in here. That big gap is because nothing is in here. We can't put helium anywhere along here because it doesn't act like the column underneath it. So the periodic table ends up being 18 columns wide. And the reason why lithium isn't over here next to helium is it acts like hydrogen, so it was then put underneath. And we keep stacking them across until we find a new one that acts. And here's sodium acts like lithium, and magnesium acts like beryllium, and aluminum acts like boron. And so that's why it has this weird shape. We also have these 2 rows down here. We're not going to use these in grade 9s, but they actually fit right in here. So all these here, the lanthanide series, this whole group here gets stacked like a deck of cards right here where this single asterisk is. And this row here all gets stacked on top of each other like a deck of cards, and it goes right in here. Now, the periodic table, so as I mentioned, it is ordered by the atomic number, and the atomic number is the number of protons in the nucleus. Each element has a symbol. The symbol for hydrogen is H. The symbol for helium is He. You'll notice that everywhere on this periodic table, they all start with a capital letter. If it has one letter, like hydrogen, potassium, moving over here, boron, carbon, nitrogen, oxygen, fluorine. If it has one letter, it's just a single capital letter. If there's 2 letters, then the second one, like in lithium and beryllium here, will always be lowercase. And we do actually have a few down here, and there are more than these that are not on this periodic table. And these have 3 letters, but once again, the first one is capitalized in the symbol, the rest are underlined, or sorry, not underlined, they are lowercase. Sometimes it makes sense. H for hydrogen. Can't use H for helium because H is already used, so we use HE for helium, and NE for neon, and AR for argon. That makes sense. Well, what about gold, Mr. Mitchell? Why are we not using G or GO? And the reason there is that some of these have been named after their Latin roots. So gold is aurum, A-U-R-U-M in Latin. Over here, we have lead, Pb. It's actually plumbum, P-L-U-M-B-U-M, I believe. That's the Latin spelling. So sometimes when the letters have already been used up, their Latin spellings or their Latin roots have become the basis for the naming of them. That is that. Till next time, take care, everybody.